The classic situation for testing the difference between means in dependent samples is the usual before or after situation, where you want to improve or reduce something. Let's take a look at the try-it-yourself problems. There's 2 of them in section 8.3 of our textbook. The first one says a shoe manufacturer claims that athletes can decrease their times in the 40-yard dash by using the manufacturer's training shoes. The 40-yard dash times of 12 randomly selected athletes are measured. After the athletes have used the shoes for 8 months, their 40-yard dash times are measured again. The time in seconds is listed in the table below at alpha equals 0.05. Is there enough evidence to support the manufacturer's claim? And we get to assume the times are normally distributed. I've made a little table and fed it to a spreadsheet. And so we've got the before times and the after times and calculated the differences. And most of them show that the athletes are running faster. Couple of exceptions. Now, in the book, they teach you a fancy formula for computing standard deviations. I'm not going to do that. If I have these 12 numbers and I feed them to my calculator will very happily tell me what the mean is for the differences and what the standard deviation is for the differences. So I've got a mean of, let me write this down, d bar, or average d, or average distance, is 0.0233. All right? And the standard deviation, and it's a sample standard deviation, for these 12 numbers is 0.0607. All right? So let's use those numbers and go ahead and compute our statistic. The statistic is a t-statistic, and it's simply the observed mean minus the hypothesized population mean over SD and divide by the square root of the sample size. We know the sample size is 12. Now let's recall what the claim is. The claim is that the athletes will do better. All right? So that's basically saying that the average for the population mean is going to be positive. Okay? And this is the claim. And obviously, it doesn't have an equal sign in it. So our null hypothesis will be that the population mean for the population of differences will be less than or equal to 0, and the claim is the alternative. Okay, so that's what we have. We know that alpha is supposed to be, for this test, 0.05. And we know the degrees of freedom will be 12 minus 1, or 11. What does this give us? Well, if we look at our t-distribution, the null hypothesis is 0 or below. So we can pretty much decide that we need a one-tail test up here, 0.05. And for 11 degrees of freedom, if we look this up, our critical number right here, our t-statistic, is going to be 1.330. All right? So when we compute our test statistic, we've got 0.0233, subtracting population mean, well, that's 0. That's assuming no change. And down below we have 0.0607 divided by the square root of 12. And we end up with a number that's very close to 1.330. Okay? And I see that I just made a terrible mistake, because that's not our critical number. That's the plotted value of our t-statistic. Alpha 0.5 actually corresponds to, I should have looked this up and really checked it, it's actually 1.796. So I apologize for that mistake. So 1.33 is down there, 1.796 is up here. We are not in the rejection region. Fail to reject, which is unfortunate for the claim of the shoe manufacturer, because the claim was in the alternative. Now let's look at the second try it yourself problem. A medical researcher wants to determine whether a drug changes the body's temperature. 7 test subjects are randomly selected and the body temperature of each is measured. The subjects are then given the drug, and after 20 minutes, the body temperature of each is measured again. The results are listed below, and I have done the little table again. And this time, we've got the 7 subjects, and the difference in the temperature, and the average, the D bar, comes out to 0.55714, and the standard deviation, again, it's a sample, is 0.9235. So I will note those down. Let's talk about what we have for our null hypothesis. The claim, of course, is that the drug changes the body's temperature. Okay? So the null hypothesis is there is no change. And the alternative is that it's something new, it's something different. By the way, I hope you notice this automatically means we're talking about a two-tail situation. So that's what we're going to expect this time. If you draw your t-distribution and you look at the two tails, and remember there's only 7 subjects, we're supposed to do this at the 5% level of significance. We have 7 subjects, so degrees of freedom is 6. And if you look for the rejection regions, we're going to have minus 2.447 and positive 2.447. Two-tailed test, 0.025 above, 0.025 below. All right? Now, I did tell you that I had computed certain values. In particular, I found out that D bar is 0.5771, and I computed SD, which the calculator will happily give us as 0.9235. What's our test statistic in this case? Well, once again, we're going to take D bar, we're going to subtract, that's supposed to be a subtraction, mu d, population d, SD over square root n. When we put everything in here, 0.5771, again minus 0, over 0.9235 divided by the square root, this time of 7, and it works out to 1.596. Well, if you check that out, 1.596, that's not at all in the rejection region. So, fail to reject the null hypothesis. And what does that mean in this instance? It means that at the 5% level, we don't have enough evidence to conclude that the drug actually does affect the body's temperature. We can't conclude that there's evidence for change.